Hello physics students. In the last physics video, you learned all about the concepts of what momentum is and what impulse is. So remember, momentum is a vector of mass times velocity, and it represents kind of like the effect of something in a collision. And impulse was force times time. More force over more time gives you more impulse. So it's kind of like the effort you put into accelerating something. And then we learned the big idea was that impulse was equal to change in momentum. And we learned about a lot of concepts about impacts and forces and times and how those vary in various impacts. But today what we're going to do is we're going to concentrate on the calculations, the mathematics behind this idea that impulse is equal to the change in momentum. So we're going to do a calculation example together. Here it is. Impulse calculations, the name of the topic for today, and here's what we're going to analyze. We got a tennis player hits a .056 tennis ball 40 meters per second at a stretched rubber sheet, and the ball bounces back at 35 meters per second. If the contact time was 0.022 seconds, determine the following things: the change in momentum, the impulse, and the average force during the collision. All right, so if you didn't keep up writing this down, I'm going to create a pause to give you a chance to copy this down. Okay, so let's move on to the analysis. So on the reference table, the formula for impulse is on the back, page 6 of the reference table. And so I just want to call your attention to the fact that it's somewhere around here where my finger is, and you could see J equals force times time, which equals delta P. So we learned that yesterday. What I'm going to do is transfer that onto the whiteboard here, but I want to add another term that sometimes it's convenient to just write out what the change in momentum is. Remember, the change in anything, the change in velocity, is, for example, the final minus the initial. Same thing with momentum. It's change in momentum is the final momentum, the final mv, minus the initial mv. And P equals mv is also on the reference table. I won't go back to show you because basically you could find it yourself. So this is often convenient when you're solving the problems to write out what the change in momentum actually is. So I just want to make that point. But before we proceed with the calculations, we have to think about a very important idea, and that's that in this topic, we're dealing with all vectors. In the last topic of energy, everything was a scale or just a number. So for example, if an object had 20 joules of kinetic energy when it was going this way, if it was going this way, it would also have 20 joules. There was no negative kinetic energy. But with momentum, we're dealing with velocities, momentums, and forces, all vectors. Direction is absolutely critical, and it must be factored in. So I've got a diagram of this tennis ball coming at this rubber sheet. Now, if I call this 40, I'm actually calling it positive 40. The plus is implied. When the ball bounces back, it's the opposite direction. So I can't leave this positive 35. I've got to indicate that with a minus sign. This is absolutely critical because your answer will not come out just the wrong sign. It'll actually come out to be the wrong numerical value if you plug in positive 35. So critical. Now we fill in what delta P is, as I said, mv final minus mv initial. So we take the mass given, the final velocity, not final speed, which is negative 35, minus the initial mv initial, which was positive 40. And if you punch that on a calculator, you get negative 4.2. If you don't believe me, put a positive here, evaluate the result, and you'll see you won't even get 4.2. It's not like you get, oh, if I leave the minus in, I get negative 4.2. If I put it in, if I leave it off, I get positive 4.2. No, you get the wrong number altogether. So critical to put that minus in. So there's the answer. And remember, momentum is not renamed like when we had newtons times meters with energy, we called that a joule. Momentum, we do not. It's left as kilograms, meters per second. That's the unit. Cumbersome, but that's just the way it is. You've got to leave it that way. All right, the next part, we want to find the impulse. And you might say, well, impulse is force times time. They told me the time, but what's the force? Oh, I can't solve it. You can, because you may not be able to do this, but we just calculated this, and all three things are equal. So you can take any two of these and set them equal to each other. J equals delta P if you'd like. Force times time equals delta P. J equals force times time. Any two, because they're all equal, so we can skip right to J equals delta P. We have the delta P, and therefore that's the J. So that's the answer there. All right, so let me create a pause and allow you to copy this down. Okay. Okay, so continuing on, the part I just erased, the last thing, we knew the time was 0.022 seconds, and now we want to know the force. So that's part C. So now that we know this is negative 4.2, we could use this part of the formula. J equals force times time. In other words, negative 4.2 kilograms meters per second. By the way, you could change this to Newton seconds if you want. If you prefer Newton seconds, that's fine. You could have put Newton seconds anywhere here. They're equivalent, so you could interchange them. I'll just leave it as kilogram meter per second. What is the force? And I believe the time was 0.22 seconds, but let me double check because I erased it. Yes, it was. And then, if you divide both sides by 0.022 seconds, you will get F equals negative 191 newtons. Why negative? Again, think about this. Well, actually, maybe before I talk some more, let me give you a chance to catch up if you need it. Okay, so why the negative in the force? If this ball is going this way, which way must you strike it, or the rubber sheet strike it in order for it to go that way? The force has to go like that, right? If it's going this way, positive, and the force is positive, that's hitting it from behind. It's going to make it go even faster. So if we want it to reverse direction, we got to hit it in the opposite way. That's why we've got the minus sign. All right, so there's our calculation, but I do want to make one final point. We could, in theory, stop here, but I also want to show you that supposing the problem didn't ask for A or B, it did not ask for the change in momentum, and it did not ask for the impulse. It just gave us the data, which you could go back and read, of the mass of the tennis ball, the initial speed, the final speed, and it asks, and the time, and it asks for what's the force? Just one calculation. You don't have to do all those steps. So let's say if what you could do is you could take that formula, and on the reference table, it was this, right? So use the part that you need. This part, we don't need the J, so we're just going to write our formula as force times time. We're looking for the force, we got the time. And rather than write delta T, I strongly recommend you just start off with a formula like this, as I said earlier. It makes it easier. Spell out what delta P is. So there's my formula. That's what I'm starting with. And so I plug in what I had, the 0.022 seconds, and then the mass of the tennis ball, 0.056 kilograms. The final velocity, not final speed, final velocity negative and then the initial velocity, positive 40. And then punch away on your calculator and get the answer as negative 191. Okay. So if you need a moment to catch up, let me create a pause so you can write this down. Okay, so again, this is, if they didn't ask for J, they didn't ask for delta P, they just directly gave all the data that I had over here and asked for force. Do it in one step. Force times time equals mv final minus mv initial. Get the answer. So that's impulse calculations. Remember, you use any part of the formula that's convenient, right off the reference table, and be very careful with signs. That's very important. If anything should reverse direction, you got to make it a minus sign. If you're plugging in a force that was given, think about it. You're hitting a tennis ball. Okay, it's going this way, and then you're going to hit it that way. Oh, I got to put a negative force in because I'm going to hit it the other way. If I put a positive force, tennis ball is going like this, and then I hit it even faster in the forward direction. So think carefully about signs before you start crunching numbers. All right, so that's it for today. I hope you enjoyed the video. I'll see you in the next physics video.